All right, let's jump right into this explainer. Today, we are unpacking a vulnerability that's been silently lurking in almost every Linux machine for, well, nearly a decade. Welcome to a crazy story about how a bunch of completely innocent code updates just kind of converged into one of the stealthiest, most reliable exploits we have ever seen in modern computing. Officially, it's tracked as CVE-2026-31431, but you'll hear the security community calling it copy fail. Now, think about this for a second. A tiny 732-byte Python script, that's it. And it achieves a 100% reliable, zero-day container escape. We aren't talking about some massive, complex payload needing a whole team of hackers to deploy. No, this is literally just a few lines of code that effortlessly bypasses standard security measures, giving an attacker ultimate root access over basically every Linux machine shipped in the last 10 years. And the blast radius here is just staggering. Researchers actually went and verified this exploit across all the heavyweights of the Linux ecosystem. Ubuntu, Amazon Linux, Red Hat, SUSE, they all just fell to the exact same script. Why? Well, because the kernel crypto API is enabled by default pretty much everywhere, meaning any machine running a kernel between 2017 and this brand new patch is affected right out of the box, no custom tweaks required. So, we've got a lot of ground to cover to really understand this threat. Here's our roadmap. Section 1, 732 bytes to root. 2, the ultimate stealth exploit. 3, poisoning the page cache. 4, a decade in hiding. And finally, 5, patching the vulnerability. Okay, moving right into Section 1, 732 bytes to root. The absolute minimalism required to pull this off is exactly what makes it so terrifying. There's no complicated compiled C code you have to worry about dropping on the box. An attacker literally just needs Python 3.10 and a few standard libraries. OS, socket, and ziblet. That's the whole shebang. It needs absolutely zero network access, zero kernel debugging features. All they need is an unprivileged local user account. By default, the script targets a common binary like /usr/bin-su to just corrupt it and hand over the keys to the kingdom. Which brings us to Section 2, the ultimate stealth exploit. Now, if we contrast copy fail directly with notorious past bugs, think Dirty Cow or Dirty Pipe, the difference is kind of scary. Usually Linux local privilege escalations need you to win a race condition, which is a messy, crash-prone timing window, right? You might get 30 to 80% reliability on a good day, and you usually need really specific per-distribution offsets. But copy fail? It's a straight-line logic flaw. It fires perfectly exactly when asked with 100% single-shot reliability. It either works or it doesn't. And on affected systems, it always works. But here's the true nightmare for system admins. Nothing hits disk. Because this malicious write bypasses the standard file-saving process entirely, the Linux kernel never actually marks the manipulated memory page as dirty. So the corruption is never saved back to the hard drive. That means your standard file integrity monitoring tools, the ones calculating checksums on your hard drive to spot tampering, they are completely blind to this. The file on the physical disk literally hasn't changed at all. Let's dig into how it actually does that in Section 3, poisoning the page cache. To really get this attack, we need to understand the page cache. Think of a system file on your disk as a master blueprint, right? And it's locked safely in a vault. Going to the vault every single time is slow. So the kernel creates a page cache, a temporary, lightning-fast copy in memory that acts like a working photocopy sitting on your desk. When a program runs, the system reads from the photocopy, not the vault. Well, copy fail doesn't try to break into the vault. It just casually scribbles 4 controlled bytes directly onto your photocopy. And here is exactly how an attacker manipulates that photocopy in 4 distinct steps. First, they open an AF-alg socket. This is just a standard way for users to access the kernel's crypto stuff without needing special privileges. Second, they construct the write, using a system call called splice to basically feed the page cache of their target file directly into this crypto process. Third, they trigger the write. And fourth, execute the corrupted binary. Boom. With those 4 simple steps, an unprivileged user manipulates the target file right in memory. The actual logic failure here is almost hard to believe. It all centers around a specific cryptographic wrapper called offensin. When this algorithm rearranges sequence numbers for processing, it essentially uses the destination memory buffer as a temporary scratch pad. Well, the bug causes it to scribble 4 bytes of controlled data right past its intended boundary. And because of how the attacker set up that socket we just talked about, that boundary crosses directly into the working photocopy, the page cache, of our target binary. It literally injects malicious shellcode straight into memory. So how did this happen? Let's look at Section 4, a decade in hiding. It was really this fatal cascade of code commits spanning years that created the perfect storm. Look at this timeline. Back in 2011, the auth and sends algorithm was added, and that scratchpad behavior was totally harmless at the time. Then, in 2015, the AF_alg socket gained support, allowing it to read from the page cache. Still not exploitable. But then, in 2017, an in-place optimization was introduced just to speed things up, combining the read and write memory locations. Every single one of these updates was completely reasonable on its own, but together they slowly aligned to connect that scratchpad bug directly to the page cache. And what's wild is that this flaw sat perfectly invisible to human code reviewers for 9 whole years. It wasn't until researcher Taeyong Lee had this sudden aha moment about how the crypto subsystem interacted with the page cache. He then fired up an automated AI-assisted security scanning tool called Extinct Code to audit the massive Linux crypto codebase. Driven by that human intuition, the AI scaled the search and found the exact path to this vulnerability in just 60 minutes, literally an hour. All right, let's fix this thing. Section 5, patching the vulnerability. We really need to delineate who needs to panic right now and who can maybe take a breath. If you're running Kubernetes clusters where the page cache is shared across the entire host node, an attacker in one single container can escape and compromise the whole node. High risk. If you run CI build servers or shell as a service platforms, same thing, extremely high risk. Untrusted code becomes root. But, on the flip side, if you're just on a single user laptop where you are already the admin, the risk is way lower. It's really just a local step up at that point. For your immediate remediation strategy, patch right now. The kernel update literally just reverts that 2017 in-place optimization, pulling those memory locations apart again. If you absolutely cannot reboot to patch today, your immediate mitigation is to disable the algif AID module. For untrusted container workloads, you should definitely block AFLG socket creation using seccom. And don't worry, disabling this module is not going to break your major crypto pathways. Your Lux disk encryption, your SSH connections, standard TLS, they'll all keep functioning perfectly because they don't even use the specific interface. So as we wrap up this explainer, copy-fail really highlights the insane complexity of modern operating systems, where totally isolated, sensible updates can accidentally weave together to hand attackers a master key. But it also shows a massive shift in how vulnerabilities are found. You really have to ask yourself, if an AI tool, guided by just a bit of human intuition, can surface a decade-old, perfectly reliable root exploit in just an hour, what else is currently hiding in your codebase, just waiting to be found?